without further ado, our next talk is by Josh Bowman Matthews, and he is going to tell us about everything. The talk's title is Everything is an Operating System If It Tries Hard Enough. Let's give him a hand.
So, heads up, I'm going to lie to you. I'm going to describe simplifications of the real world, like Naomi talked about this morning. Sometimes, like, models are hard, the real world is complex, and we need to simplify them down. I'm going to do this because it's complex, and I think there is still value in learning things that are technically wrong. So the first lie is that everyone knows what an operating system is. I mean, I'd hazard a guess that everyone here has used one regularly, but I doubt everyone here actually would feel confident trying to define what it is. I mean, maybe even the people willing to try wouldn't even agree. And even the people who agreed, I mean, they might not even be correct. So what does it actually mean to be an operating system? We're all familiar with them, so let's try and reverse engineer a definition by looking at the common elements of the most popular desktop ones: Windows, macOS, and Linux. I mean, to start with, they all provide some sort of graphical interface. There's lots of windows, there's lots of folders to interact with. Great. Next, you've got hardware. If you write a program for any of these platforms, you don't have to care about whether the user has a Bluetooth or a USB mouse. You don't need to write special code to handle like a particular gaming keyboard or different kinds of hard drives. These differences are all hidden from developers by the operating system under layers of abstraction. Another common feature of these, they all run programs. I mean, there's no inherent way to execute code on a computer. It's up to the operating system to actually kick off the process and tell your CPU what code needs to be executed. And finally, all of these systems enforce rules. There are different users, there's different privileges, running programs need to be isolated from each other. None of these properties actually hold unless the operating system enforces them. So we've got a list of 4 fairly broad properties of mainstream desktop operating systems. However, there are more kinds of operating systems that we need to consider. We can't claim to define an operating system if that definition doesn't hold for old ones as well. I mean, consider Windows 3.1. It had a graphical user interface, but on the other hand, DOS was famous for putting you like right in a terminal. And meanwhile, you have embedded systems like free RTOS, which may actually run on a CPU and not give you any kind of like input-output mechanism that way. Similarly, many older or specialty systems may not provide guarantees around isolation. But they all still run programs, and they still provide some level of abstraction away from the direct hardware. So what we're left with is a concept of an operating system. It's something that runs programs in an abstracted environment of some kind. We can actually think about the operating system like the Big Bang in astronomy. Before the operating system, there's nothing. After the operating system, there's something, and that something can run programs. But what does it actually mean to run a program? Fundamentally, a program is a sequence of computations. What is the purpose of a computation, though? Spoiler, there's no purpose. Programs have no inherent meaning. They're nothing better than the waste heat generated by mining bitcoins. Computation is just a program screaming into the void. However, what gives a program meaning is when these screams can be heard. That is the role of the operating system. The computation is meaningless unless the result of that computation can escape that void. This happens through something called a system call, where a program asks the operating system to do something that the program cannot actually do on its own. So opening a file, printing a character, making a network connection, we think of these as features of the programs we write, but it's actually the operating system which is doing the heavy lifting here. The system calls available to programs vary across operating systems, but they tend to be the lowest level of abstraction that is required in order to uphold the rules of that operating system. Because those rules would not matter if the program could actually just choose to ignore them. So we've gone a little deep into questions about the nature of computing, so let's take a break and let's talk about a program called Megazooks that was released in 1994. Megazooks is interesting to me because it's actually playing a video. Why is it not playing a video? Well, if it was playing, you would watch a little like smiley face character moving around. It would be really janky, nice 1994 gameplay. But the point is, it's a game creation system. It allows users to create their own simplistic games from scratch. It comes with its own programming language called Robotic. Rather than a single program that controls the entire game, MegaZooks games are made up of many smaller programs that run concurrently. Each individual torch, like this one and this one, that's displayed here in this game is actually its own program that changes its color and display to look like it's flickering. This is one example program of robotic. Robotic is an imperative language with no blocks, no functions, no structured programming, just labels and go-to and commands that can modify the current game state. Almost all variables are global and they can store numbers. The command set temp to 0 here stores the number 0 in a variable named temp. We can also pass a string like PromptConf instead of the number 0, and that would set temp to the current value of the variable named PromptConf. So in 1996, the source code to MegaZooks was released, but there was a catch. Somehow, the original author, Alexis Jansen, she had lost the source code for the robotic editor and compiler, but she didn't lose the compiled object file for that part of the system. And so this actually meant that as long as you used the exact version of Borland Turbo C++ from 1996 that was used to compile that object file, you could compile the rest of MegaZooks and link it all together into a final executable. And this state of affairs persisted for most of a decade, with every developer passing around a link to an FTP server where you could download that right version of Turbo C++ if you wanted to make changes. And so this imposed some interesting limitations on how MegaZooks could evolve, because it still exists. It has kept changing. We were stuck with the existing set of commands in robotic and couldn't add any new ones. Also, we couldn't change what kind of arguments those commands accepted. Strangely enough, that didn't actually prevent robotic from evolving. So first, game developers said that they wanted to make games that relied on mouse, like on the mouse input. Since mouse coordinates are numbers, it seemed reasonable to add some special variables that could always contain the current mouse coordinates, named mouse x and mouse y. Great. Next, game developers said they wanted to make games that used the system clock, whether for building timers or Easter eggs related to dates. I mean, they're all still just numbers, so using more special variables that were hooked up to the system clock seemed reasonable. You could use date month and date day and time hours, they're all just numbers. After that, developers wanted more complex math in their games. The kind of math operations that it would have been really nice to have like special separate commands for, but that was impossible. So the answer was more special variables. In particular, we introduced a min and max operation that took two numbers separated by a comma and would return the appropriate one based on the operation. It was awkward, but clever. But game developers were not content. They wanted to follow best practices and separate their games or their game assets from the game itself. And this required being able to access files programmatically. And so again, this would have been a great place to add a new command, but instead, we never let perfect be the enemy of barely good enough, and we added more special counters in like really backwards ways, but it worked. You could open a file, you could close a file. That's all you really needed. So the immediate lesson here is that the strings can contain anything, and so they're a very convenient way of extending the capabilities of a language. But if we zoom out a bit, there are a couple interesting properties about MegaZooks. Fundamentally, it's a system that runs programs that happen to be games. These games need to interact with the environment outside of the game. And the mouse, the system clock, the files, and the system gave the programs the access they needed through an interface that it controlled. So it turns out that's an operating system, according to the definition we came up with earlier. Let's take a look at some other ones. So web browsers, they load lots of different web pages. Those web pages, they're really just programs that happen to be HTML and CSS and JavaScript, and they make lots of requests for things like network access and persistent storage and audio. I mean, the web browser is responsible for making these features available to these programs through JavaScript APIs. Turns out that's an operating system just for web pages. What about Google Spreadsheets? It's got a lot in common with an operating system, it turns out. Imagine that a spreadsheet is actually a program. All of the computations happen inside cells that have formulas in them. Some mathematical formulas, like the ones here, can be completed without any additional help. They're simple, math operations. Other ones, like this bizarre import XML formula, can access data from a remote arbitrary data source, and that needs the help of the runtime for these spreadsheets. In other words, that's an operating system. And yes, the physical printer on your desk is an operating system. Because you know how documents get from your computer to the printed page. It's pretty cool, actually. The program you run, that you print your document from, converts the document into a PostScript program. That program then gets sent to your printer, which runs this program, and your printer understands how to use commands like show page, which will take the vector graphics and turn them into pixels that we plotted with ink on the page. And turns out that is an operating system as well. So really, I promised you a bunch of lies here, but it's actually only been one lie. It's an excessively vague definition of an operating system, and everything else just sort of follows from that. That doesn't actually make me wrong, though. Everything is clearly an operating system when you start looking closely at the details. So in conclusion, I strongly encourage all of you to start lying in order to help computers make more sense. Thank you.